Hi, Calc AB. Welcome back. Good to see you all again. Well, I mean, I can't really see you, but you know what I mean. Today we're going to talk about some things with the second fundamental theorem of calculus, and we'll probably take a look at a few different kinds of ideas behind it. And I wanted to make sure that we hit this specifically because College Board has chosen this as a means of emphasis for a lot of the exam in the past few years. It sort of came in a while ago, but it's really taken off in the last few years. And so not really understanding what the exam is going to look like this year compared to last year, because last year's was such a weird test. I want to make sure that we have a pretty good foundation on second fundamental theorem. So this week, one of the things we're doing is a worksheet on it and a couple of other things that go with second fundamental theorem. And let's just take a quick peek at a few things about the second fundamental theorem of calculus. And so the first thing I want to do is, oh my, that's some statistics. We don't want that. Sorry about that. We're gonna be talking about the second fundamental theorem of calculus, and I got to admit, Dr. Larson kind of sells it a little short in our book. His version of the second fundamental theorem says, okay, so if you take the derivative with respect to x of the integral from a to x f of t dt, okay, you're going to get little f of x. And okay, yeah, I mean, that's definitely an interpretation of the second fundamental theorem of calculus, but I feel like it falls a little flat. It's a little bit on the short side. So even though that's exactly what theorem 4.11 says on page 282, there's just so much more to this than meets the eye. And so I want to make sure that we really get a good understanding of this. So first thing I would say is this is a very simplified version of the second fundamental theorem of calculus. There's some pretty important ramifications of the second fundamental theorem of calculus, and so we want to really dig in there and investigate all those things. So first things first, I don't particularly like this version of it because that upper limit being x, again, kind of sells it short. Now, let's take a look at how this works. I'm going to go back and use that idea from the first fundamental theorem of calculus that, little f of x has an antiderivative that we call capital F of x, okay? So what we're really saying in here, if I kind of go through the first fundamental theorem, is we're deriving capital F at x minus capital F at a. And so, thinking back to our derivative rules, then that means we can split this up and we can take the derivative of each half of this difference individually. So we could take the derivative with respect to x of capital F of x minus the derivative with respect to x capital F of a. Uh-oh. I kind of went off screen there, sorry, but you get the idea. Now, up at the top, if little f has the antiderivative big F, then if we derive big F, what do we get? We get back to little f of x. So that's why we get little f of x here. And then we have to remember that f of a is a constant. So f of a will also be a constant. And so when we derive that constant, it, as I like to say, derives away. Its derivative is 0. And so we're at the end, we end up with f of x, little f of x, just like we saw. But what I mean by this being overly simplified is that, why did it work that way? Well, it worked that way because the upper limit was just x, okay? And we were going from a constant, to x. And so what I've seen the College Board do, and our book does this a little tiny bit in the section, is it makes it a little bit more interesting, okay? It adds a function like so. Now, okay, so how does that change what we're doing with the second fundamental theorem of calculus? Well, again, I'm going to go the route I'm going to kind of go through that first fundamental theorem, and so I'm going to say, okay, well, let's take the inside of this grouping symbol and realize that that would be capital F of g of x minus capital F of a again. Aha! When I take the derivative now, of course, f of a, right? Let's just, we all agree that this guy, when you derive, is going to go to 0, right? Because it's a constant. What happens to capital F of g of x, though? You got it. You got to use the chain rule. And that's where I think our book falls flat, is it doesn't really emphasize that very much. Yeah, if you want to take the derivative capital F of g of x, that's fine. But you have to remember capital F's derivative, little f, leave the inside function alone, right? Then the chain rule says, oh, wait, you're not done. Multiply that by the derivative of the inside function. So if you're integrating from a to g of x of little f of t dt, and then you're deriving that, like a second fundamental theorem of calculus says, well, then you have to remember the chain rule. You're going to get little f of g of x times the derivative of that upper limit. Okay, and that's where I feel like Dr. Larson kind of lets us down a little bit. What if the bottom one is the one that has a function? Well, then you're subtracting a little f of whatever that function is times the derivative of the inside function. So, if we're deriving from g of x to a f of t dt. Well, if you go my way, which is through the first fundamental theorem, you're going to see that that is the derivative with respect to x of capital F of a minus capital F of g of x. And then we derive that, and of course we get 0 minus little f of g of x times g prime of x. Of course, chain rule. So definitely want to be paying attention to where the function is. Now, there is that nice little rule where you could have said, oh, you know what I'm going to do? I'm going to make it negative so that I'm going from a to g of x of f of t dt. Well, okay, same thing, right? Because now you get the negative of capital F of g. You get it. All right. So last but not least, what if there's functions on both top and bottom? Well, then obviously, right, you have double chain rule. G of x to h of x, little f of t dt, right? So that's going to give you little f of h of x times h prime of x minus little f of g of x times g prime of x. Yeah, so Dr. Larson, thank you for your theorem, but man, you kind of missed the boat on how complicated College Board's going to make this. And yes, they do this. They have done this on the AP exam. And so I want to make sure that, yes, if we scroll back here a little ways, Dr. Larson's theorem is technically correct. Okay, yes, this is true. But the fine folks at the College Board have found ways to really complicate things by adding functions top and bottom and making sure that everybody's paying attention to the chain rule as we go along. So that's one of the first things I wanted to talk about with you with second fundamental theorem of calculus, because I've definitely seen College Board do this to us. So when we work on the stuff that we're going to do here, second fundamental theorem wise, this is a big piece of it. However, there's also another important ramification from the second fundamental theorem of calculus, and it's a little more subtle. It's that we've never really seen a function defined in this way before. We've never seen a function defined as the antiderivative of another function, right? Usually our functions have been like, here's f of x, right? Well, now what we're saying is, look, the function of x is actually the integral of another function. If you look at just this part right here, we're actually defining a function as the integral of another function. And that has some pretty big ramifications for us down the road. So we're going to take a look at some of what that might mean, okay? Because the area model that we've been using now helps us define then some of the aspects of our new function. And so let's take a look at a little bit more on what that might mean for us. And so I'm going to start off with a pretty simple idea. I'm going to just say, look, the integral from, let's say, 1 to 3 of f of x dx is 7. And let's say the integral from 2 to 3 of f of x dx is equal to 5. And let's do one more. Let's have the integral from 1 to 3 of g of x dx be -2. So what I'm going to do here is look at, first thing, how do these things impact some of other functions that we might talk about? Like, what if I had, the integral of, 4 times f of x dx on the interval from 1 to 3, right? Well, clearly, right, we could move the 4 out front and go from 1 to 3 of f of x dx. And well, we know that the integral from 1 to 3 of x is 7. So this is 4 times 7. So this is 28. Okay. Or we might say, well, how about this? How about the, I'm going to clear the, I got to erase that. What about the integral from 1 to 3 of f of x plus g of x? Right, well, that's the integral from 1 to 3 of f of x plus the integral from 1 to 3 of g of x. And we get 5, okay? So as you think about these things, try to envision what's happening with the functions, right? That way, when you see one that you're like, oh, I don't know what that is, right? Try to picture it in your head, like what is happening, or even draw it out. What's happening with that function, so that when I say, okay, well, I'm going to do this. I'm going to do f of x minus 2 dx from 3 to 5. Okay, well, what does x minus 2 being inside of f of x actually do, right? Well, we know from our work on parent functions that moves it to the right 2 places. Okay, notice what I did with the limits as well. I moved those to the right 2 places. Okay, so yeah, this is still just going to be 7. Make sense? Picture what's happening with the function, and you kind of see how that's going to work. Okay, what if I don't include the 2 in the parentheses, right? What if I do something like, I say, well, let's do this. Let's integrate from 1 to 3 f of x plus 2 dx. What is that doing to the function? Oh, that's lifting the whole function up 2 units, right? If you picture that in your head, like what happens if you do that? Okay, we're going to look at it on a graph here in a minute. But yeah, what am I adding underneath? Well, it's 2 units high and it's 2 units. So I'm adding 4. So I know that I'm adding 4. So this is going to be 11. Now, you actually could do this using the first fundamental theorem of calculus, because you could say, oh, well, actually what I'm doing is I'm going from 1 to 3 of f of x dx, right? That's 7, we know that. Plus, hey, you could integrate from 1 to 3 of 2 dx, right? That'd just be 2x. So we know we've got 7 plus 2x evaluated from 1 to 3. Well, if you plug in 3, you get 6. You plug in 1, you get 2. 6 minus 2 is 4. So this is 7 plus 4, just like I said. So we get 11. So you could do it. You could figure it out that way as well. But I like to think about what's going on in the graph. Okay, because I think what's going on in the graph makes a huge difference than trying to algebraically. Of course, we can figure it out, but I think we could see it visually. Okay, so here's what we're going to do. We're going to define a new function here, and I'm going to share a graph with you. Okay, here's my graph. And what I'm going to do is I'm going to define a function here. Hang on, I got to slide some windows around here so I have some room. Okay, and I got my annotation tool here. So what I'm going to define is this is the function. Let's call this function f. Okay, and I'm going to define my function g of x to be the integral. I'm sorry, I wrote an x on the f. I think that should be a t. There we go. This is the t-axis. Sorry, the graphing software I use can only do x-axis, but it's a t-axis. And my g of x is going to be the integral from 2 to x of f of t dt. And this is the part of the second fundamental theorem that I feel like really gets glossed over a lot. That we are now, now that we've seen how area works and we've been able to kind of attack some area problems and use it, I'm going to define my function g of x as the integral of f of t dt on the interval 2 to x. And now, using the area idea, I'm going to come up with some values for g. For example, could you come up with g of 0? Right? Well, yeah, let's look at the area model for a second. Let me draw in here. Here's 2. Oops. Yeah, kind of didn't get that perfectly vertical, but you get the idea. Okay, so what does the area look like underneath f of t dt? Right? Well, I made it pretty simple. They're straight lines for this one. So you can see if I want to go g of 0, I'm going to go from 2. And notice I've got 1, 2, 3, 3.5, 4. Okay. So I know the area under the curve is 4, but notice that's the integral from 2 to 0 of f of t dt. Well, normally we integrate from left to right. So can you flip it? Sure. So what's g of 0? It's -4. Because I know the area underneath there is 4. Okay. Oh, yeah. Hey, what's g of 2? The integral from 2 to 2, right? Anytime the limits are the same, that's got to be 0, right? Yeah. Check that out, right? So now we're starting to see how can we use the area model plus this kind of cool implication of the second fundamental theorem, this function defined as an integral. Okay. And we can start figuring out some values of our function. What if we said, hey, I know, how about what's g of 4? Well, that's the integral from 2 to 4 of f of t dt. Oh, from 2 to 4. Let's see. I've got area 1, 2, half, 3. So that's 3. So we've got a few points now on our function g. Okay. What's g of 5? Well, look, you just add on this little half here and you go, oh, okay, yeah, that's 3.5. And how about g of 6? Oh, well, this half here now, right? That's a negative 1/2. So we're back to 3. Hey, by the way, anybody notice that f is the derivative of g? So what do we have at x equals 5 on the function g, right? It's got a relative maximum right there. Yeah, yeah, pretty cool. We know that because the derivative is changing sign from positive to negative. And if you look, 3.5 is bigger than the other sides, right? It's got to go up. Whoa, I didn't mean to put that little mark in there. So, yeah, that is our one of our cool implications of this particular part of the second fundamental theorem is using this area model. We can come up with different ways to think about our function g. Yeah, pretty good stuff. All right, so now that we've played around with the function g, which as we said earlier in the video here, we were talking about messing with g, and that was here's f of t again. Sorry, I had to clear this off on my t-axis. I'm going to define another function now. And this time, what I'm going to do is, as I was mentioning earlier, I'm going to try shifting this around a little bit so that we can now visually see how that shift changes the function. So I'm going to define a new function. This time it's going to be h of x. And h of x is going to be the integral from 2 to x. All right, so just like g, of f of t. But here's what I'm going to do. I'm going to add 3 to our function. Okay, so what is really happening in this is that this whole thing here, okay, is going to get lifted up 3 units, right? You can see what I'm saying. Like if I take my graph here and I lift it up 3 units, basically the x-axis, or the t-axis, I guess in this case, is going to drop all the way down to here, right? So here's our new origin right here. This is 0, 0 now. And so, when I had those values that I found earlier, like g of 0, right, was -4. Well, now look what happens. I've got all this same area that we had before, right? We had this one, and this one, and this one, and this one. But what have I added on? All of this area down here, okay? I've added on 6 more, okay? And so by adding the 3, lifting the whole function up, this is what I was talking about earlier, that graphically in our heads, what we want to see is we're adding all this area underneath our function. Or if we lower the function down, right, we're bringing it down. We can move the x-axis up or down, okay? And we can really see then what's happening to our function. So h of 0, okay, if I want to find h of 0, okay, well, that's the integral from 2 to 0 of this function, f of t plus 3 dt. Well, I knew this was going to be -4, so I'm just going to add this on down here, which is a -6 more. So we know we're going to get -10. Okay, and that's the idea with the graphical part of this, is looking at that area model and saying, oh, okay, so when I find h of 3, I could look at the old area that I had, which was this one, this one. Well, just add on 3 more down here. Okay, I think I have found g of 4 before, right? Which was 1, 2, and these 2 makes 3. Well, now I'm adding on 6 down below. So the graphical visualization of that adding of 3 in the integrand, translates over to adding on, from 0 to 6, which is all we know about our function here, right? We've basically added these 18 units below. Okay, now we have to be a little careful because from 2 to 6, right, we have, 1, 2, 3, 4, these 12 units that are going to be positive, right? And then from 2 backwards to 0, we have these 6 units, which are going to be negative. Down here, this is a -6 down here. And so just keeping in mind the direction that we're moving is going to change the sign of some of that area. But the whole idea is that lifting this thing, this graph up 3 units, we can then understand that there's going to be this, 18 more units of area somehow underneath it. And whether they're positive or negative, that depends on what the limit looks like. Okay, but that's part of this idea with the second fundamental theorem of calculus, not so much the second fundamental theorem itself, but that function defined as the integral of another function. All right, we're going to take a look at something different now. All right, I'm going to take you to an oldie but a goodie. You'll probably recognize this graph. Boom. Back in week 14, we had you take a look at this graph. And the idea back then was just to use what we had learned about the first derivative so far to kind of figure out what the graph of this might look like. And I said something interesting in the warm-up. I said, let's assume this is a derivative graph. So now what I'm going to do is I'm going to say, okay, this is f of t, this is f of t. Okay, and all right, and I'm going to define g of x to be the integral from 0 to x of f of t dt. All right. And actually, what I said was in the slide of the warm up for week 14, I said, okay, this is f prime of x. We know f of 0 is 0. Now let's make a sketch of the graph as best we can. Well, I'm essentially saying the same thing now, but now that you know what antiderivatives are, it's a little easier to write this problem out in a way that College Board most likely would. Notice that it still is, I'm still saying 0 is 0, right? F of 0 or g of 0 is 0, because g of 0 is the integral from 0 to 0 of f of t dt, which of course would be 0. So I know g goes through the point 0, 0. Okay, let's find some other key points along the graph. For example, could you find g of 1 now? Sure. What does the integral from 0 to 1 of f of t dt look like? Well, what's this right here? Well, that's a triangle, right? It's got a height of 2 and a length of 1. So that's area of 1, but it is below the x-axis, so it's -1, right? Now be careful, because let me get back to my blue pen here. G of -1, wrong blue, oh well. Right, over here, that's also an area of 1, and it's below the x-axis. Okay, but remember, I'm going right to left, so that area turns positive. Okay, you can flip the limits if you want, put a negative sign in front of the integral, and then you see it's negative of -1, so it's +1. Okay, and then we just kind of keep going. Can you find g of 2? Well, sure, right? G of 2. Let's take a look, right? Oh, look, we have another triangle here. Yeah, that's an area of 1 triangle. So for g of 2, we're back to 0, right? G of -2. Well, that's also going to be 0, right? Because here's another triangle. right? But we're going backwards. So, we had a positive one area down here in the blue. So that red area is going to be -1. So we're back to 0 as well there. Okay. Yeah, so g of 0 is 0. G of 2 is 0. G of -2 is 0. You're starting to see what's happening here, right? Yeah. Now, how about G of 3? Now we have a rectangle in here, right? So we could say, oh, well, look, that rectangle is 1 unit wide and it's 2 units tall. So G of 3 is going to be 2. And G of -3 is going to be -2. It's kind of nice that I have a nice symmetry in our graph here, right? And so at the end of the day, you can get a good picture of what this function looks like by using the same kind of logic as before. Okay, because we know what the mins and maxes are going to be. We know where it's linear. We know where it's curved. We know that from -2 to 2, right? The first derivative is increasing, so it's got to be concave up. We know from -2 to 0, it's got to be or from 0 to 2 and this is concave up, from -2 to 0 it's got to be concave down. We still know all that stuff. Okay, but we're now able to actually put some y coordinates to the picture. So far so good. Making sense here. I hope so. Oops, I gotta clear my drawings there. All right. So now that we've got a clear graph again, just wanted to imagine like what would happen if we changed our function again. So this time, my annotation tool disappeared on me. Here we go. This time I'm going to find a new function, h of x. And this time I'm going to shift my graph the other direction. So last time I shifted it by adding. This time we're going to shift the graph down. And so what I'm going to do is I'm going to say, well, this is the integral from 0 to x of f of t minus 2 dt, just to kind of show you that, I can shift up or down, left or right. It doesn't matter how we shift it. We just reorient our axes and then we can still follow along with the same area models before. By subtracting 2, what essentially ends up happening is we get a new x-axis up here. And you can see now, oh boy, come on. Sorry, the computer's running a little slow. I've got a couple of different tasks going at once. So all of those areas are now below the x-axis. Okay, so we see that this function is decreasing the entire time, with the exception of -3 to -2 and from 2 to 3, where we have, flat lines, but and the slope there is 0. So, this still provides you with a nice way to come through and think about, okay, what would some y coordinates look like? Obviously, h of 0 is 0. But what does h of 2 now look like, right? Oh, come here, where's my pen? H of 2, right? Well, that's the integral from 0 to 2 of our function. And notice that the entire thing is below the x-axis now. So this whole area here is now a negative area as I go from left to right. Now, the area of that triangle, right, is 4, because it's got a base of 2 and a height of, going down here of 4. So I know that that's got -4 area. Okay. As I go from, h of 2 to h of 3, it's still -4, right? Because there's no area in here. That is just right on the x-axis. So there's no area between the function and the x-axis there. Okay. And then as I start to go from 3 to 5, right? we're going to have another triangle here of area 4, but it's below the x-axis. So h of 5 then will be -8. Okay, because below the x-axis all the way down to this point here. So because remember the axis has moved up here. This is our axis now. Okay, going the other direction, what's h of -2 going to look like? Well, this triangle down over here, it still has area of 4, right? But remember, when we go from right to left, the signs change, right? So that's why this is the negative of -4. Okay, because it's -4, but we're going backwards. So you get +4. H of -3, again, we have that flat line right there, so there's no area added on there. And then over here, of course, we have another -4 area below the x-axis, but we're going right to left still, so you get negative. So h of -5 is going to be +8. And so the effect, again, of moving that axis, if you draw the picture or try to visualize it in your head, and maybe it's easier to just kind of sketch it out like I do, so that you can really see how the area is affected by the shift in the functions. The second fundamental theorem of calculus looks so basic, especially the way Dr. Larson presents it, but it has some pretty profound implications. From what we talked about earlier, in terms of you could complicate the derivative by changing the upper function from x to be a function of x, to adding a function on the bottom, and then we have to make sure we remember the chain rule, to the idea that, oh wow, we can actually define a function as the integral of another function. And that's a pretty big one for us too. So anyway, thanks so much for watching, guys. I apologize for the video being kind of long, but I did really want to make sure we hit this idea pretty hard. So have a great weekend, everybody. I'll see you in class if you're in my class, if you're in Miss Hoagie's class. Thanks for watching. Hopefully you got some good information out of this, and we'll see you in class next week.